Hi everyone, we're Junyu Yin and Yangzhe from CS657, mining massive datasets. Our final project is called Big Data Classification for Fraud Detection, and in the next 5 minutes I'll show you how we used PySpark to keep a massive fraud pipeline both scalable and accurate. Here's the roadmap for the talk. I'll start with why fraud detection is still a huge deal, then walk through the EECIS dataset, the Spark architecture we built, how we pre-process and rebalance the data, the models and evaluation results, and finally the takeaways. Global digital payments blew past $9 trillion last year. That means even leaking 0.1% in fraud is catastrophic. Fraud cases make up only about 3.5% of transactions, and the feature space has over 400 anonymized columns. With that imbalance and dimensionality, accuracy alone is meaningless. The question we set out to answer is whether a distributed Spark pipeline plus targeted resampling can keep recall high without drowning analysts in false alarms. That's why we optimize precision recall AUC and closely track false negatives. We're using Kaggle's EECIS dataset, 590,540 transactions, and 434 engineered features. We join the transaction and identity tables on transaction ID, tackle heavy missingness, and respect the 96.5% legitimate to 3.5% fraud split. With 64 megabyte partitions and mindful caching, the Spark pipeline runs in roughly 14 minutes on our 8-core, 16 gigabyte lab node. Everything flows end-to-end inside main.py. The loader ingests pre-processing and advanced encoding transform, the imbalance handler resamples, the models train and evaluate, and visualization exports the figures. One Spark job reruns the entire pipeline. For pre-processing, we drop columns with over 70% missing, impute numeric values before scaling, and fill categorical gaps with a literal missing token. Low cardinality features get one-hot encoding, mid-cardinality features get frequency or smooth target encoding, and the huge ones go through hashing. Then, to address the imbalance issue, we randomly undersample the legitimate class down to roughly 2 to 1 while preserving every fraud example. That shrinks the training set from about 600,000 rows to 13,000, cuts training time to minutes, and adds roughly 5.8 PRAUC points versus skipping resampling. Model-wise, we keep logistic regression as the transparent baseline, then rely on ensembles for lift. The random forest uses 100 trees, depth 10, and 80% subsampling. The gradient-boosted tree runs 100 iterations, depth 5, with a 0.1 learning rate. A threefold Spark cross-validator tunes everything against PRAUC. We also export feature importance, so the compliance team can see top drivers like transaction amped, card fingerprints, and the target-encoded p-email domain. Gradient boosting secures the top PRAUC at 0.578, while random forest edges ahead on overall accuracy, 93.7%, and macro F1, 0.947. These bars represent class-weighted performance on the full test split. Legitimate transactions maintain precision above 98% across all models, but the fraud class separates the contenders. Gradient boosting records 30.4% precision and 74% recall. Random forest sits at 30.8 and 65.6%, and logistic regression falls to 17.5 and 48.6%. The table explicitly labels the classes to remove ambiguity. Gradient boosting dominates the high recall region and stays above random forest, while logistic regression declines rapidly. All models exceed 0.8 RAKUC, but the ensembles climb faster for the same false positive rate. Gradient boosting captures 2,282 frauds, misses 800, and raises 5,233 false alarms, approximately 1% FPR. Random forest reduces false alarms to 4,536 but detects only 2,023 frauds, illustrating the precision, recall trade-off. Both ensembles elevate transaction amount, card fingerprints, and the target-encoded email domain. To wrap up, the distributed PySpark pipeline now runs end-to-end in about 14 minutes. Random undersampling plus gradient boosting deliver more than 5 PRAUC points and 6 percentage points of recall over the naive baseline, and the modular code means we can swap encoders or models quickly. Next on the roadmap is an anomaly detection prefilter to reduce scoring latency, SHAP on Spark to add explainability, and tying the models into a registry for continuous training. That's all. Thank you for your attention.